Hi, welcome to our short courses on physics and chemistry. We've called them crash courses, and our intention for this is to fundamentally focus on some of the calculations, mostly the typical problems you can expect to see in an exam. Obviously we can't do every single type of problem there is, but we've tried to put together as I say, the most typical ones that you can get. Now, I'm not going to go through a lot of the theory because unfortunately we don't have time in the crash course to do that. That is part of the whole lecture series that some of the students have already done with me. However, just before we start, please remember and learn the laws, Newton's laws of this and that and whatever, Ohm's law. Learn those laws because you know what, they're marks and they will be asked. State this, state that, and right up until grade 12, you're going to be asked state this law, state that law, etc., etc. So please take the time to learn that, and some of the, as I say, we will cover some of the elements of theory. Right, so let's get going with question 1. What they've given us here in question 1 is they've given us a scenario. They've given us a few forces acting on a body, and they've said, calculate the resultant of the following system of forces acting on A. A is a body. It's this or something else, right? There's a whole lot of forces acting on this. What happens to this? There's a hint. They've said calculate the resultant force, which means that there's an imbalanced force in there somewhere. What is the resultant? The resultant is essentially, it is the one force that we can replace all the other forces with. It's analogous for those of you who are good with perhaps electricity to taking a parallel resistors, and what do? We use a formula to calculate the effective resistance. It's a similar analogy. The resultant force is the same. It's the one force that does the same job. It's the same as the one resistor that does the same job as a whole bunch of other resistors in your circuit, right? So let's have a look and see, right, what have we got? Let me just draw it quickly. It would help if I had the pen. There we go. We've got 10 vertical. We have got 100 newtons that way, and you've got this with you, so 40 degrees up there. We've got 150 newton force up there, and that's acting up at 30 degrees over there. There's a 45 down there degrees and 50 newtons over there, and lastly a 20 newton acting down here. Okay, and this in the middle here is point A. All right, as I say, let's pretend it's this, shall we? This little bag. First of all, whenever we've got something which has got forces at an angle, we have to resolve it into the various components. That's the critical part. The components of that are the ones that we can add vertically and horizontally. And remember, the components are the sine and the cos elements. So let's take ourselves 100, we can leave him because he's already just horizontal. So let's look at the 50 newton force, shall we? 50 newtons out that way, and it's at 40 degrees up like that. And let me just change to a different color. There are our components, right? That's the 90 degrees. How do we do it? Stand at the angle and look out. Opposite means sine. So opposite, that's the sine one. So it's 50 times sine of 40 degrees, which means this is 50 times cos of 40 degrees. And we can work those out. I've already done it, and it's going to be vertical 32.14 and horizontal 38.3 newtons, like so. Okay? Then we can move along. We say, right, let's have a look at our other guy. Let's have a look at our 150 newton. 150 newtons this way, and that's at 30 degrees. I didn't take the 10 newton vertical because it's already resolved. It's vertical, right? So we just leave it. Only the ones at an angle are we going to be resolving. So let's go and say, okay, red, just put that in, and there we go. Stand at the angle and go opposite. So this is going to be 150 times sine of 30 degrees. 150 times cos of 30 degrees. Let's work it out. 150 sine 30 is going to be 75 newtons, and that's going to be 129.9 newtons. Okay, then we've also got a force which is this 50 newtons force, haven't we? We've got him, and he's coming down into quadrant 3 over there, and that's at 45 degrees there, and that is a 50 newton force. Okay, red, there we go. Okay, have a look, I'm adding them nose to tail here, right? Can you see that? There's my components. I haven't chosen a direction yet. Remember I said that. That's going to tell me which way to point these arrows. This one's going to be down. Okay, so let's have a look. This one is going to be 50 times opposite, which is the sine. So that's going to be 50 times the sine of 45 is 35.36 newtons there. And this one, 35.36 newtons that way. Now we say, okay, we've resolved all of our forces into their various components. So let's just move up slightly, because then what we're going to do is we're going to put them all together again. How do we do this? We say, first of all, we look at all vertical forces. Let's have a look here. Let's look at all the vertical forces, okay? Right, we've got our 32.14, let's go. We've got this one, 32.14, and then we can tick it off, right? We've got that one, 32.14, which is the vertical force there. 32.14 newtons. Then we've got the 10 newtons, okay? Then we've got the 75 newtons. Then moving around, we've got one going down, 35.36 newtons. Then going down, we've got 20 newtons, right? Let's just check those out. There we go. Can you see? Let's go around. 32.14 is this guy, isn't it? Okay. Let's just put it in blue. That's him. We've got that force. Okay. We didn't need him, so we've got his component. We've put the 10 in. The 150 vertical is upwards. There's this little arrowhead, is upwards. The 50 is a 35.36 down, and then there's a 20 down. So we've got all our forces. So if we add 32.14 plus 10 plus 75 minus 35.76, we get a single force at the end of the day of 61.78 newtons, like so. Okay? Then we do exactly the same with the horizontal. We say, okay, all horizontal forces. Okay? And we do the same thing. We go vertical, or rather we go to the right and we go to the left. So if we do that, we've got 100 newtons going this way. We've got another 38.3 going this way. And we've got going this way, 129.9. And this way, 35.36. Okay, newtons. All right, let's just go and check we've got everybody. Okay, we've got the 100. Let's just tick it off. There we go. We've got the 100. We've got this one. There we've got that guy going that way, haven't we? 38.3, right? Then we've got the 150 going this way is the 129 and that. So we've only got 4 going that way, right? And there we go. There we've got them there. Now we can go back and say, okay, let's add them. I always say to the right positive, but it doesn't matter. Just add them and see which way the resulting one goes. You end up with a force going that way of 26.96. Right? When you've added that plus that, minus that, minus that. You end up with that. It might have a minus sign, but that just means it's going that way. So we've got 2 forces, haven't we? We've got 2 forces like that. 61.78 newtons and 26.96 newtons. Now we want to find the resultant, okay? And this is going to overlap a little bit, but please bear with me. Okay, I always say, right, I move this one and I add it nose to tail, so I know my resultant is going that way, and my R is going to be equal to the square root of 26.96 squared plus 61.78 squared, which is going to be equal to, and if you work it out, it comes to 67.4 newtons. Okay? So that's what we've got. The last bit is, remember, it's a vector. Vectors have got directions, right? A magnitude and a direction. So what do? I'm now going to put in the direction of this vector and say, right, I need to work out. I know that height there is 61.78, so therefore theta is going to be arctan of 61.78 divided by 26.96, and that's going to give us 66.4 degrees. Alright, so what have we done? We've now found the resultant force on our bag of all of the forces that were acting. Essentially, it's a force that is going to be pulling the bag up that way, right? So the bag is going to be moving off in that direction, right? There's nothing holding it. Just a little bit of theory. The equal opposite force to that is going to be acting in that direction, and that would then be called the equilibrant. Because what is that force? That would be the force that holds the bag in place, wouldn't it? That'll be this force here that keeps it from moving away. So the equilibrant is the opposite in magnitude and direction to your resultant. Okay? Now, that's the typical vector problem. The next one I want to look at is a three-force problem. Okay? Now, in the three-force problem, we've got the one you're looking at is you may have, and you're always going to have three strings or three somethings attached to each other, right? In this case, we've got a string and a weight hanging down here, which is the classic one. But you can see there's three strings that are tied at a knot, right? Now, in this case, they've said A and B are connected as shown, all right? Let's just draw it quickly. Just move this up a little bit. Okay. Let's go to page 2. So let's just draw it. Okay. There is our wall. Okay. And we've got a string going down here. Got a string going up there. And they've given us some angles of 30 degrees, and they've given us an angle of 40 degrees there. Right? And they've said some weight is box, or something's X is hanging down over there. All right? This is how you always approach these. First of all, you do a separate drawing of it. So you do your little free body diagram. We say, right, what have we got? In essence, we're looking at this knot. We say this has got a mass over here. So we always put in the weight is equal to mass times gravity. G is 9.8. So FW is 9.8 m. Okay? Then we look up and we say, okay, I've got a force over here, and let's call this B, and it's a thing, so let's call it tension in B because it's a string. Okay? FB is also fine. Let's call this TA, tension in string A. Right? And let's put in the angles over here. This angle is 30 degrees, and this one over here is going to be 50 degrees because that's 40. Okay? So we've now got forces at an angle, and what is the recipe for that? Resolve them into their components. Let's just do that. You notice we've hardly even read the question yet. Okay? TB is opposite, right? So that is TB times sine of 30 degrees. That one is TB times cos of 30 degrees. Okay? TB sine, TB cos 30 degrees. Let's work that out as a number. What is it? Well, I've done it up ahead, so let's just go to save time. This is 0.5 TB, and this is 0.866 TB. Let's go to the opposite side, okay, and put in this one here. This one is going to be horizontal, is going to be TA cos of 50, which is 0.6428 times TA. This one is going to be TA times sine of 50 degrees, right? Which is 0.766 times TA. Okay, dokes? That's what we've got for that one. Now, What do we know now? Here's the key. It's in equilibrium, which means the forces pulling me up are equal to the forces pulling down. Forces pulling this way equal forces pulling that way. If somebody's pulling me this way and this way equally, I'm not going to move, which means I'm in equilibrium. There's two sides to mechanics. The first side is something's in equilibrium, which means total vertical must equal total up must equal total down, total right must equal total left. Right? That's what it says. That's equilibrium. So let us put the total to the right equal to the total to the left. In other words, we're going to be looking at horizontal forces. So let's look at horizontal forces. Now we know left must equal right because of equilibrium only. Okay? There's no unbalanced force here. So if I go to the right and the left, what we can say is 0.866 TB. Okay, do you know what? I've done it. Let me just do it the opposite way. 0.6428 TA must be equal to 0.866 TB. Okay? Therefore, TA must be equal to, you do 0.866 divided by 0.6428 because that goes over. Oops. Okay. This goes over here. Okay. So what have we got here? We've got TA is equal to 1.347 times TB. That means that when we put a weight on there, it means that the force in A, okay, is going to be 1.347 times bigger than the force in B. Because it's carrying more of the load, right? It's carrying more of the weight by virtue of its angle, let's say. Okay? That means that if you look at it, if TB was 100, TA is going to be bigger, isn't it? Which means no matter what you do, TA will be the one that breaks first. Therefore, TA will always be more than TB. And what does that mean? It means, therefore, TA will break first. Right? Obviously, because that's the one carrying more load. It's carrying 1.3 times the load that's in B. Right? Now they've said the maximum load that they can carry is 500. Therefore, TA is 500 newtons. Therefore, TB must be what? 500 divided by 1.347 is 371.2 newtons. Just go through that. They've said the maximum it can carry is 500. Therefore, the TA is going to be 500 because that's the biggest one it can be. Then therefore, TB is going to be 500 divided by 1.347. Okay? Now we move along and we go and we say, okay, now total vertical forces. And remember, up must equal down. So what do we say? We say, right, total up. In this case, we've got, let's just have a look. Just get it. Total up is going to be 0.5 TB plus 0.766. 0.5 TB plus 0.766 TA must be equal to 9.8 times M. Right? Okay, happy with that? 0.76, 0.5 TB. Now you know what TB is. Right? So we can now work it out. Let's have a look. 0.5 times 371.2 is equal to 185.6 plus 0.766 times 500 is 383. Okay, must be equal to 9.8 times m. Therefore, the maximum mass m is going to be that plus 185.6, just adding those two, equals that, divided by 9.8 is equal to 76.9, right, something like that. Just check, 0.5 times, yeah, it's going to be 76.9, 77 kilograms or so, something about there, right? 0.766 times 5, let me just check, 0.766 times 500, yep, 383, and 371.2, we know that guy is there, so therefore we get 77 kilograms, okay? That's what we can put on there as a maximum weight, okay? Now, that's the typical one. What you do is when you've got the three forces, you've got 1, 2, and 3, they could be the other way. For example, let's just before we close off, you could have forces like this, okay, where this could be TA and TB over here. Something could be pulling up of 100 newtons, for example, right? It's just the same three-force problem, and all you do is you resolve each of the forces, the unknowns, into their components, because they are forces at an angle, and then what we do is when they're component, you put total up must equal total down, and total to the right must equal total to the left. That's the equilibrium side of these. Next we're going to move on and we're going to look at using Newton's law. We've got F equals ma. That's the next phase of this. So the key of this, equilibrium. If it's an equilibrium, total up equals total down, total to the right equals total to the left.